The most dire outcome imaginable for 3i Atlas sounds fantastical until you consider a different perspective. What if its departure is not the actual event? What if this flyby path is, in reality, a calculated reduction in speed, accomplished by technology beyond our present detection capabilities? Envision an intelligence so sophisticated that replicating natural orbital movements is mere child's play. A civilization that deploys observational instruments cleverly disguised as celestial bodies like comets, asteroids, or even discarded space junk. The extraordinary velocity and peculiar chemical makeup of 3 Atlas might not be indicators of its natural origin, but rather of intelligent design and purpose. As it draws nearer to its closest point to the Sun, hidden systems could be activating, preparing for the subsequent stage of whatever mission brought it to our vicinity. Tonight, we will delve into the uncertain territories where conventional explanations falter and cosmic apprehension begins to take hold. The crucial inquiry isn't whether 3 Atlas will depart, but rather whether we will perceive its decision to remain. Part 1. Is 3 Atlas a menace? On the first day of July in the year 2025, Chile's Atlas telescope identified something remarkable, a faint point of light exhibiting a hyperbolic trajectory, which could only signify one thing. This visitor originated from an entirely separate star system. Identified as 3 Atlas, previously known as C2025 None, it stands as humanity's third verified interstellar entity, following Oumuamua in 2017 and 2i Boris in 2019. But what if this third traveller carries implications far exceeding those of the initial two? Implications that redefine the very concept of a worst-case scenario. Unlike bodies native to our solar system, constrained by elliptical orbits, 3 Atlas follows a hyperbolic course through space. Its orbital eccentricity surpasses 1, definitively marking it as unbound by the gravitational pull of our Sun. Accelerating inwards from the constellation Lyra at unprecedented speeds, it is projected to reach its perihelion on October 29th, at a velocity exceeding 130 miles per hour, fast enough to traverse the continental United States in under 3 minutes. Yet, beneath these reassuring mathematical certainties, a persistent question lingers. What if the true worst-case scenario isn't about its destination, but about what it might expose regarding ourselves? Despite its dramatic speed, 3 Atlas poses absolutely no danger to Earth. Its closest approach in mid-December will be approximately 1.8 astronomical units away, roughly 270 million kilometers, nearly twice the distance between Earth and Mars at their closest alignment. NASA's stance is unambiguous. This is a naturally occurring comet, not a manufactured craft or a hazardous object. But when we venture beyond NASA's carefully worded pronouncements into the realm of conjecture, what hidden aspects might this ancient wanderer cast upon our assumptions about intelligence, intent, and cosmic coincidence? The Hubble Space Telescope has been observing the visitor since its discovery, revealing typical cometary behavior as solar radiation vaporizes ices within its nucleus, generating a luminous coma. The James Webb Space Telescope captured spectral data on August 6th, indicating unusually high concentrations of carbon dioxide, a chemical signature indicative of extraterrestrial formation conditions dissimilar to anything within our solar system. However, this chemical anomaly provokes an uncomfortable question. What if the ultimate significance of 3 Atlas lies not in its identity, but in what it compels us to confront about our own ignorance? Ground-based observatories across the globe have joined the endeavour, with radio telescopes detecting only natural emissions and silence where artificial signals might reside. This coordinated effort exemplifies modern astronomy at its finest, a global network confirming both the object's interstellar origins and its harmless trajectory. But what transpires when we move beyond the comforting boundaries of harmlessness and contemplate scenarios that challenge not our physical safety, but our fundamental comprehension of our position in the cosmos? The rate of discovery suggests that space teems with such wanderers, fragments from planetary formation around distant stars, expelled into the void by gravitational forces and destined to roam for eons. Each imparts new knowledge about the galaxy beyond our sun's influence, though none imperils our world's safety. Yet, if the galaxy is indeed populated by these ancient emissaries, what are the implications when we dare to speculate beyond the established scientific consensus? As The Guardian aptly observed, 3 Atlas is a cosmic curiosity, not a catastrophe, a reminder that we inhabit a universe far more peculiar and interconnected than our daily lives suggest. This ancient visitor grants us a brief glimpse into the profound history of the galaxy, carrying secrets from stellar environments we can scarcely conceive. But what if the real enigma isn't about the secrets it holds, but about the secrets it might unveil concerning the true nature of interstellar travellers and the speculative possibilities that lie beyond the reach of our telescopes? Part 2. Speed, Size, Age, a Quiet Powerhouse. The sheer numbers alone are astounding. 3 Atlas travels at speeds exceeding 130 miles per hour, approximately 150 times faster than a high-velocity rifle projectile. Its hyperbolic excess velocity of 61 kilometers per second represents the speed it maintains even after accounting for solar gravity, unaffected by eons of galactic drift. But when we consider what such incredible velocities might enable in speculative scenarios far beyond current scientific understanding, what possibilities emerge that could fundamentally alter our definition of a worst-case scenario? This speed dwarfs its interstellar predecessors. Oumuamua travelled at 26 kilometers per second, while 2I Boris managed 32 kilometers per second. 3 Atlas moves at nearly twice that pace, suggesting either a violent ejection from its home system or acceleration through multiple gravitational interactions during its cosmic journey. Yet, what if this progressive increase in velocity across 3 interstellar visitors hints at something more intentional than random cosmic upheaval? Something that propels us towards speculative realms our instruments cannot probe. Determining its size presents a challenge due to the luminous coma that obscures the nucleus. Current estimations range from 0.3 to 5.6 kilometers in diameter, a span encompassing anywhere from 3 football fields to a small mountain. The uncertainty arises from assumptions regarding surface reflectivity and coma production efficiency. Smaller estimates appear more probable, based on typical cometry parameters, though even at 0.3 kilometers, we're discussing a significant object. But what if the very ambiguity that frustrates our measurements conceals possibilities that extend far beyond mere questions of dimension? This uncertainty in size raises intriguing questions about survivability. How could such a relatively modest body withstand ejection forces followed by millions or billions of years in interstellar space? Smaller objects face greater vulnerability to tidal disruption and high-speed collisions with cosmic debris. Yet, what if the resolution to this puzzle of survival opens doors to speculative scenarios concerning durability, purpose, and design that transcend naturalistic explanations? Most intriguingly, 3 Atlas likely possesses extreme antiquity. Analysis suggests origins within the galaxy's thick disk, an older stellar population from a time when the Milky Way was young and turbulent. If accurate, this visitor could predate our entire solar system by billions of years, carrying within its nucleus records of galactic evolution from an era when the universe was less than half its current age. But what if this ancient origin story becomes the bedrock for speculative scenarios that challenge our very understanding of time, purpose, and cosmic intelligence itself? The thick disk interpretation stems from the object's motion relative to galactic rotation. While most local objects move in sync with the galaxy's spin, 3 Atlas approaches from an unusual angle, suggesting membership in an older, more randomly oriented population, stellar elders whose orbits have not been tidied by billions of years of galactic evolution. Yet, when we venture beyond astronomical interpretations into speculative territory, What might this unusual approach angle imply about intentionality, navigation, and purposes that extend beyond natural orbital mechanics? Despite its tremendous speed and mysterious past, 3 Atlas poses no dynamic threat. The very hyperbolic trajectory that identifies it as interstellar guarantees its safe passage. It travels too swiftly for capture by our solar system, with its closest planetary approaches measured in astronomical units, not kilometers. But as we prepare to explore the shadows beyond scientific certainty, what if the genuine worst-case scenarios have nothing to do with physical impact and everything to do with what this visitor might represent? Observation windows present difficulties. Its peak brightness, around magnitude 11, requires significant telescopic power even under ideal conditions. During its closest solar approach, the object vanishes into the sun's glare precisely when becoming most active. Cosmic timing that feels almost cruelly coincidental. Yet, what if this observational limitation becomes the very gateway to speculative scenarios where what we cannot perceive holds more significance than what we can measure? What emerges is a portrait of cosmic resilience, ancient, swift, and ephemeral. 3 Atlas embodies the confluence of impressive physics and minimal risk, reminding us that the universe operates on scales that dwarf everyday experience, while adhering to laws precise enough to predict this visitor's location years in advance. But when we dare to inquire about what lies beyond these predictable paths, what speculative worst-case scenarios arise that bear no relation to orbital mechanics and everything to do with cosmic revelation? Part 3. Chemistry in the Quiet. CO2 Overdrive. When Webb's infrared instruments examined 3 Atlas on August 6th, they revealed something extraordinary: a coma dominated by carbon dioxide, with a carbon dioxide to water ratio of approximately 80:1. This was not merely unusual, it was unprecedented in cometary chemistry. But as we prepare to move beyond chemical analysis into speculative domains, what if this molecular signature hints at purposes and origins that far exceed natural formation processes? Typical comets follow predictable patterns. Water ice is predominant, sublimating at moderate temperatures to produce characteristic water vapor comas mixed with dust. Carbon monoxide appears next, followed by carbon dioxide and trace compounds. The ratios of these molecules tell stories of formation conditions and evolutionary history. Yet, 3 Atlas has entirely rewritten this narrative, exhaling carbon dioxide as if engaged in industrial-scale atmospheric production. And what if this deviation from the norm opens the door to speculative scenarios that challenge everything we assume about natural versus artificial origins? The numbers become even more striking when considering the observation distance. 3 Atlas was over 3 astronomical units from the Sun, well beyond Mars, when Webb captured its spectrum. Most comets exhibit little activity at such distances, yet this object generated a detectable, carbon dioxide-dominated coma, extending hundreds of thousands of kilometers from its nucleus. But what if this inexplicable activity at improbable distances becomes the foundation for speculative scenarios concerning energy sources, internal mechanisms, and purposes that transcend our current understanding of natural possibility? Several theories attempt to provide explanations. 3 Atlas might have formed near its parent star's carbon dioxide snowline, where this compound preferentially condensed from the protoplanetary disk. Alternatively, extreme age and cosmic ray processing could have altered surface chemistry, creating radiation-processed crusts that seal in water while allowing carbon dioxide to escape. A third possibility involves insulating dust layers that developed over geological time, acting like cosmic insulation that prevents water access while permitting the percolation of more volatile carbon dioxide. Yet, what if all these natural explanations, however plausible, miss the most unsettling possibility? That this chemical signature represents something deliberately engineered for purposes we cannot yet comprehend. Webb's near-infrared spectrograph detects molecular fingerprints with exceptional precision. As sunlight warms the coma, molecules emit light at specific wavelengths, revealing their chemical composition. The observed 80:1 ratio represents one of the most extreme carbon dioxide enhancements ever recorded in cometary observations. But when we venture beyond spectroscopic measurements into speculative realms, what if these molecular signatures encode information that extends far beyond simple chemistry? Messages, perhaps, or indicators of purposes that challenge our assumptions about cosmic intelligence. This is not entirely without precedent. Comet C 2016 R2 Pan stars also displayed atypical volatile ratios, with unusual concentrations of carbon monoxide and nitrogen. Such chemical outliers suggest either a greater diversity in cometary formation than theories have assumed, or significant post-formation processing that altered surface compositions. Yet, as we approach the realm of pure speculation, what if these chemical anomalies across multiple objects hint at a pattern, a signature that points toward possibilities existing beyond the comfortable confines of natural explanations? The value of 3 Atlas lies in its representation of chemistry from entirely different stellar environments. While pan-stars formed under conditions we can model, this visitor carries chemical signatures from processes around different stars, possibly billions of years ago. Extraterrestrial geology delivered to our doorstep. But what if this delivery is less accidental than we presume? And what speculative scenarios emerge when we consider that ancient intelligences might have devised ways to encode information within the very chemistry we're now detecting? Ongoing observations will determine whether the carbon dioxide dominance represents bulk composition or surface expression. As solar heating intensifies, molecular balance may shift if water ice lies beneath carbon dioxide-rich surfaces, potentially revealing deeper compositional layers through changing thermal penetration. Yet, what if these shifting chemical signatures as 3 Atlas approaches perihelion reveal patterns that suggest not random heating, but systematic activation, opening pathways to speculative scenarios of dormant systems awakening under solar influence? This chemical detective story extends beyond the specifics of 3 Atlas. If interstellar objects routinely exhibit exotic compositions, then planetary formation around other stars produced a wider variety of icy bodies than exists in our system. The carbon dioxide-rich environment that shaped 3 Atlas might represent common conditions around certain stellar types or evolutionary stages. But as we stand on the precipice of speculation, what if these exotic compositions represent something far more deliberate? Markers, perhaps, or signatures that point toward a cosmos populated by intelligences we're only beginning to detect through their chemical fingerprints. From broader perspectives, this unusual chemistry tests planetary formation models extending beyond our solar system. If theories about icy body formation and evolution are accurate, they should account for the observed diversity in interstellar visitors. 3 Atlas challenges expectations, suggesting either theoretical gaps or simply a vast range of conditions in galactic neighbourhoods we have never studied. Yet, when we venture beyond theoretical frameworks into pure speculation, what if the challenge this visitor presents to our models hints at something more profound? Evidence of processes, purposes, and intelligences that operate beyond the natural laws we have spent centuries charting. Part 4. Worst-case scenarios answered. Nearly 2 decades into our investigation, the supposed worst-case scenario proves refreshingly mundane. No Hollywood-style catastrophe awaits. No civilization-ending impact threatens Earth. No gravitational disruption sends our planet careening toward destruction. Cold, precise celestial mechanics deliver a verdict that should allow us to sleep soundly. Yet, as we prepare to venture beyond the safety of scientific certainty, what if the true worst-case scenarios reside not in the realm of physics, but in the speculative shadows where our instruments cannot reach and our theories dare not tread? Those crucial numbers deserve repetition. 3 Atlas approaches no closer than 1.8 astronomical units to Earth, 270 million kilometers of comfortable buffer. This distance exceeds twice the closest Earth-Mars approach distance, and represents over 50 times the distance to our moon. Perihelion occurs around October 29th at approximately 1.4 astronomical units from the Sun, placing it between Earth and Mars orbits, close enough for significant solar heating and spectacular carbon dioxide coma production, but nowhere near affecting planetary orbits or raining debris on any world. But what if distance becomes irrelevant when we consider speculative scenarios involving technologies, intelligences, or purposes that operate beyond the constraints of physical proximity? These are not rough estimates, but precise orbital calculations, accounting for major planetary gravitational influences, relativistic effects, and subtle perturbations from radiation pressure. When astronomers declare 3 Atlas poses no threat, they speak with confidence built upon centuries of celestial mechanics and decades of tracking potentially hazardous objects. Yet, what if the calculations that ensure our physical safety become the very foundation for speculative worst-case scenarios that have nothing to do with collision and everything to do with contact, communication, and cosmic revelation? The initially alarming speed, over 130 miles per hour, actually works in our favour. Objects on hyperbolic trajectories moving at such velocities cannot be captured by solar system gravity. 3 Atlas moves too quickly to linger and cause trouble, performing its cosmic flyby before vanishing back into interstellar space. But what if this very speed, this inability to be captured, represents something more than natural orbital mechanics? What if it hints at deliberate design, precise timing, and purposes that extend far beyond our current capacity to detect or comprehend? This highlights important distinctions in risk communication that space agencies navigate carefully. The term interstellar carries an emotional weight unrelated to actual danger. Primitive brain responses to approaching unknown objects conflict with geometric realities. Space's vast scales and orbital mechanics conspire to make such encounters fascinating rather than perilous. Yet, what if our focus on physical danger blinds us to other kinds of risks? The speculative scenarios where the worst case isn't about what 3 Atlas might do to us, but what it might reveal about us, our assumptions, and our place in a universe far stranger than we dare to imagine. NASA's communications strike a perfect balance, acknowledging scientific significance while emphasizing the absence of hazard. Clear, jargon-free language explains why this object is remarkable without being threatening, maintaining public interest in genuine discovery while avoiding unnecessary anxiety. Previous interstellar visitors provide additional context. Oumuamua posed no threat in 2017, despite its unusual behaviour, while 2I Boris displayed predictable cometary activity during its 2019 passage. 3 Atlas continues this pattern of scientifically fascinating but dynamically harmless visitors. But as we stand on the threshold of speculation, what if this pattern of harmless visitors masks something far more significant? A cosmic census, perhaps, or a gradual revelation that challenges everything we believe we know about intelligence, purpose, and our cosmic neighbourhood. Our current understanding forms a satisfying foundation. We know its speed, trajectory, and unusual carbon dioxide-rich composition. We have evidence suggesting great age and thick disk galactic origins. Multiple world-class telescopes provide detailed observations of its chemical makeup and physical behaviour. These knowns paint a picture of an ancient, fast-moving, chemically unusual, but fundamentally natural comet. Yet, lurking beneath these comforting certainties lies the great unknown. When we venture beyond the question of what 3I Atlas is, and instead ponder what it could signify within a cosmos where intelligence might manifest in forms utterly alien to our comprehension, a realm of speculative scenarios unfolds. Significant uncertainties persist. The precise dimensions of its nucleus are estimated to span from hundreds of meters to several kilometers. Explanations for the dominance of carbon dioxide in its composition, whether stemming from surface or bulk characteristics, remain elusive. We are unable to pinpoint its birth star system or reconstruct the exact sequence of gravitational encounters that have shaped its current trajectory. Crucially, none of these unknowns impact the assessment of any potential risk. However, what if these very unknowns become the bedrock for speculative scenarios that extend far beyond the comfortable confines of naturalistic explanations? This illustrates the proper methodology of astronomical risk assessment, effectively differentiating between scientific curiosity and genuine threats. Media coverage has largely mirrored this judicious approach, highlighting both its scientific significance and its inherent lack of danger. The available visual evidence consistently supports this interpretation. Images captured by the Hubble Space Telescope reveal the classic signatures of a comet. Spectroscopic readings from the James Webb Space Telescope indicate unusual yet natural compositions. Ground-based observations track its emissions as they evolve in a predictable manner. There is a complete absence of any artificial signals, thermal anomalies, or indications of controlled maneuvers within the data. Yet, one might consider the possibility that this very absence of overt artificiality serves as a gateway to speculative scenarios involving intelligences so advanced, so subtle, that their operations elude our current recognition. Every measurement converges on identical conclusions. 3 Atlas appears to be precisely what it seems: a natural comet bearing chemical imprints from an alien stellar environment, behaving in accordance with universal laws of physics. The confirmation of this universality represents one of astronomy's most profound discoveries, and the worst-case scenario, defined by tangible physical threats to Earth, is thoroughly debunked. The mathematics are clear, the observations are consistent, and the conclusions are reassuring. This celestial visitor arrives peacefully, whether by design or by chance. But now, we arrive at the juncture where we deliberately step beyond the safety of scientific consensus, venturing into the domain of pure speculation, where worst-case scenarios assume entirely different forms, not threats to our physical existence, but challenges to our very understanding of what is conceivable in a universe that may be far more populated, far more intelligent, and far more purposeful than our current models dare to suggest. Part 5. Alien Technology or Comet. We now deliberately cross the threshold from established fact into the realm of conjecture, where possibilities multiply like reflections in a hall of mirrors. Everything that follows should be regarded as a thought experiment, not a scientific conclusion, a mental exploration of what might be, clearly distinguished from what we demonstrably know. The evidence, as we have established, overwhelmingly indicates that 3 Atlas is a natural comet. However, let us delve into the implications should that evidence prove incomplete or deceptive. The foundational understanding remains unchanged. NASA, the European Space Agency, and virtually every mainstream astronomical institution characterize 3I Atlas as a natural cometary visitor. This is not a product of bureaucratic consensus or an ingrained scientific conservatism for its own sake. Rather, it is the conclusion that best aligns with the available data. The object exhibits classic cometary behavior, adheres to predictable orbital mechanics, and displays spectroscopic signatures consistent with sublimating ices. Occam's razor, that fundamental principle of scientific reasoning, strongly favours the natural explanation. Yet, science has a history of unexpected revelations, and some of its most significant discoveries have originated from phenomena that initially appeared mundane. Pulsars were first detected as enigmatic radio signals, so regular in their cadence that they were briefly labelled LGM, standing for Little Green Men, before their identification as rapidly rotating neutron stars. Fast radio bursts baffled astronomers for years before revealing themselves as the signatures of exotic cosmic phenomena. Could 3I Atlas represent another instance where nature proves more extraordinary than our initial assumptions? The speculation surrounding its artificial origins does not arise in a vacuum. Avi Loeb, the Harvard astrophysicist who garnered attention for his unconventional interpretations of Oumuamua, has already begun to articulate similar possibilities for 3 Atlas in various interviews and blog posts. Loeb's position, explicitly labelled as opinion rather than established fact, suggests that we should remain open to the possibility that some interstellar objects might represent technological artifacts rather than natural formations. This perspective warrants serious consideration, not necessarily because it is correct, but because it exemplifies how extraordinary claims should be rigorously evaluated. What would constitute definitive proof of an artificial origin? What observations would compel us to abandon the natural comet hypothesis in favour of something more unconventional? These questions are vital for distinguishing between healthy scientific skepticism and the reflexive dismissal of novel ideas. If 3E Atlas were indeed some form of artificial construct, we would anticipate detecting signatures that set it apart from natural celestial bodies. Coherent radio emissions, for instance, could signify onboard electronics or communication systems. Such signals would need to be unmistakably artificial in nature, distinct from the random electromagnetic noise emitted by all objects, but rather structured transmissions that could not arise from natural processes. Non-gravitational accelerations that cannot be attributed to outgassing would represent another telltale indicator. Natural comets frequently exhibit minor deviations from purely gravitational trajectories as sublimating gases generate minuscule propulsive forces. However, if 3I Atlas were to alter its velocity in ways inexplicable by gas production, or if its acceleration did not correlate with patterns of solar heating, this might suggest some form of propulsion system. Engineered light curves, which describe how an object's brightness fluctuates over time, could offer additional evidence. Natural comets typically brighten in a predictable manner as they approach the Sun, with variations corresponding to their rotation periods, surface irregularities, and outgassing patterns. An artificial object might display brightness variations that adhere to different principles, perhaps indicating controlled changes in orientation or the operation of active mechanisms. To date, none of these artificial signatures have been detected in 3I Atlas. Radio telescopes monitoring the object have registered only the profound silence of space and the natural emissions expected from sublimating cometary material. Its trajectory adheres to the laws of celestial mechanics without any inexplicable deviations. Its brightness fluctuations align with the patterns observed in other comets as they rotate and react to solar heating. The prevalence of carbon dioxide, which makes 3I Atlas chemically unusual, does not in itself imply an artificial origin. As we previously explored, several natural processes could lead to carbon dioxide-rich compositions. Radiation processing of surface materials, formation in regions close to carbon dioxide snowlines within protostellar disks, or the development of insulating dust mantles could all account for the observed chemical signatures. To leap from a chemically unusual composition to an artificially constructed object would necessitate evidence that unequivocally rules out all plausible natural explanations. This is where the lessons learned from Oumuamua become particularly pertinent. That inaugural confirmed interstellar visitor ignited intense speculation about its potential artificial nature, fueled in part by its unusually elongated shape and its slight acceleration. Radio telescopes conducted extensive searches for artificial signals, yielding no positive detections. Detailed analysis of its motion revealed that outgassing from water ice could account for the observed non-gravitational forces. What initially appeared inexplicably exotic ultimately found naturalistic explanations. This pattern suggests a valuable approach for evaluating 3I Atlas, maintaining an open mind to extraordinary possibilities while simultaneously demanding extraordinary evidence. The scientific method functions precisely because it subjects all hypotheses, whether conventional or unconventional, to the same stringent evidentiary standards. Claims of an artificial origin must meet these standards, rather than merely pointing to gaps in our current understanding. Responsible reporting on these speculative scenarios necessitates clear labelling and appropriate contextualization. When media outlets discuss the possibility of an artificial origin for 3I Atlas, they should prominently categorize such discussions as speculation rather than established scientific fact. This distinction is more than merely academic. It significantly influences public perception of both this specific object and the broader scientific investigative process. The speculative discourse serves a legitimate purpose beyond simple entertainment. Considering artificial possibilities compels us to think more critically about what differentiates natural from artificial phenomena in the cosmos. It encourages the development of observational tests that could, in principle, falsify the natural comet hypothesis, and serves as a reminder that the universe may yet hold surprises that challenge our current paradigms. Future observations will continue to test these speculative scenarios. Additional spectral data as 3i Atlas approaches perihelion might reveal chemical signatures that are difficult to explain through natural processes. Precise astrometric measurements could detect trajectory anomalies suggesting controlled motion. Long-term monitoring might uncover behavioral patterns inconsistent with passive cometary activity. However, the burden of proof rests squarely on those proposing artificial explanations. The natural comet hypothesis benefits from its consistency with known physics, established cometary behavior, and the observed characteristics of previous interstellar visitors. Overturning this scientific consensus would require evidence that unequivocally demonstrates the inadequacy of natural explanations and positively supports artificial alternatives. The intellectual exercise of contemplating these possibilities should not detract from the remarkable reality of what 3i Atlas actually represents. Even as a natural comet, this ancient wanderer carries information about stellar environments we have never visited, chemical processes that occurred billions of years ago, and the deep history of our galactic neighborhood. This is extraordinary in itself, without necessitating exotic interpretations. As we continue this speculative journey, it is worth recalling that astronomy's most profound discoveries have often stemmed from meticulous observation of seemingly ordinary objects. Pulsars, quasars, gamma-ray bursts, and gravitational waves all began as mysterious signals that eventually unveiled new physics. Whether 3i Atlas ultimately proves to be a conventional comet or something more unusual, it has already expanded our understanding of interstellar space and the diverse array of objects that traverse the void between stars. The subsequent phase of our speculative exploration will venture into even more dramatic scenarios, not due to their likelihood, but because they illuminate the types of questions that arise when we encounter something unprecedented in our cosmic experience. These thought experiments will push the boundaries of possibility while maintaining clear distinctions between conjecture and established fact, between what we imagine and what we truly know. Part 6. Worst Case Speculative Scenario. A Dark Forest Trigger. We now venture into the most profound depths of speculative territory, where the shadows of cosmic possibility cast implications that would fundamentally alter our understanding of our place in the universe. What follows is purely a thought experiment, a mental exploration of implications and possibilities not supported by current evidence, but which serve to illustrate the profound questions that could emerge should our assumptions about 3i Atlas prove to be inadequate. The dark forest hypothesis originates from both science fiction and serious CT, search for extraterrestrial intelligence discourse. Drawing its name from Liu Cixin's acclaimed novel, it represents a genuine philosophical stance regarding the nature of cosmic civilizations. This hypothesis posits that advanced civilizations might deliberately conceal themselves from one another, operating under the premise that revealing one's existence and capabilities could invite predation from even more advanced neighbors. In such a universe, silence becomes a survival strategy, and any civilization that broadcasts its presence risks annihilation from threats it cannot perceive or comprehend. If we permit ourselves to imagine, and we stress this is purely imaginative, that 3i Atlas represents not a natural comet, but some form of reconnaissance probe, the implications would be staggering. Such a scenario would imply that our solar system is being surveyed by intelligences capable of engineering objects that can endure billion-year journeys between stars, while remaining virtually indistinguishable from natural phenomena. The very perfection of its disguise would indicate a level of technological sophistication that vastly surpasses our current capabilities. Consider the engineering requirements such a scenario would entail. A probe designed to pass as a comet would need to flawlessly mimic every aspect of natural cometary behaviour. The correct spectroscopic signatures, appropriate outgassing patterns that respond realistically to solar heating, and surface properties that reflect light in a manner consistent with natural ices and rock. It would need to carry sufficient volatile materials to maintain its disguise throughout its passage within our solar system, while simultaneously housing whatever sensors, processing capabilities, and communication systems would justify such an elaborate mission. The power demands alone would be formidable. Sustaining active systems across interstellar distances and over billion-year timescales would necessitate energy sources far beyond our current technological reach. Perhaps some form of radioisotope thermoelectric generator could provide power for millennia, or advanced fusion reactors could operate on trace interstellar hydrogen. The probe might even harvest energy from cosmic rays or magnetic field interactions during its interplanetary journey. But let us push this speculative scenario to its dramatic conclusion. Imagine that our continued observations of 3E Atlas begin to reveal anomalies that cannot be explained by natural processes. Perhaps radio telescopes detect brief, structured transmissions as the object traverses the outer solar system. Maybe its trajectory exhibits minute but unmistakable course corrections, suggesting active guidance. Or possibly its chemical emissions display patterns too complex and organized to result from random sublimation. The trigger moment in this speculative narrative might arrive when 3I Atlas begins to deploy secondary objects, smaller probes that detach from the main body and assume positions throughout our solar system. One might establish an orbit around Venus, another around Mars, while others scatter through the asteroid belt or position themselves at gravitationally stable Lagrange points. Suddenly, our solar system would host a surveillance network of unknown origin and capability. The question that would immediately arise: how should humanity respond? This hypothetical scenario would instantaneously become the greatest diplomatic and strategic challenge our species has ever confronted. Unlike the gradual first contact scenarios often depicted in science fiction, the discovery of an active surveillance network would confront us with the reality of technologically superior intelligences already operating within our immediate cosmic vicinity. The governance questions would be unprecedented and urgent. Who possesses the authority to speak for Earth? The United Nations, the major space agencies, individual nations with advanced space capabilities, or the scientific community that made the discovery? The complexity of achieving global consensus on something so momentous strains the imagination, particularly given our species' track record of cooperation on far simpler matters. The active SETI debate would abruptly shift from theoretical discussion to immediate practical concern. The SETI community has long debated the wisdom of transmitting signals into space versus merely listening for signals from other civilizations. Some argue that advertising our presence could attract unwelcome attention from potentially hostile aliens. Others contend that remaining silent while conducting increasingly sophisticated astronomical observations offers no real protection, as any civilization capable of interstellar travel would likely detect our technological signatures regardless of our transmission policies. However, in our speculative scenario, the choice might be removed from us. If 3I Atlas and its hypothetical secondary probes were actively studying human civilization, our response itself would become part of the data being collected. Silence might be interpreted as wisdom or fear. Attempts at communication might suggest aggression or curiosity. Even the internal debates about how to respond would reveal fundamental aspects of human nature and social organization to whatever intelligence was monitoring us. The crisis communication challenges would be extraordinary. How would one inform the global public about the presence of alien surveillance systems without triggering widespread panic? How would scientific objectivity be maintained while acknowledging possibilities that exceed our current understanding? How would one distinguish between verified observations and speculative interpretations when the stakes could involve the very future of human civilization? The scenario would likely unfold through a series of expert roundtables, emergency sessions of scientific organizations, and carefully crafted public briefings. Governments would need to balance transparency with stability, providing sufficient information to maintain credibility, while avoiding the social disruption that might result from confirming humanity's first encounter with non-human intelligence. Misinformation would become a critical concern. The mere suggestion of alien surveillance would spawn countless conspiracy theories, false flag accusations, and claims of government cover-ups. Distinguishing between legitimate scientific observations and baseless speculation would be crucial for maintaining rational public discourse on what could be the most significant discovery in human history. The technological implications would be equally profound. If 3 Atlas revealed capabilities that surpassed our current understanding of physics, it might offer insights into propulsion systems, energy generation, material science, or communication methods that could revolutionize human technology. The scientific windfall could accelerate our development by centuries, assuming the intelligence behind the probe allowed us to continue existing and evolving. However, perhaps the most unsettling aspect of this speculative scenario would be its temporal implications. If 3I Atlas had been journeying for billions of years, it might represent technology from a civilization that achieved interstellar capability when our galaxy was drastically different from its current state. The intelligence that launched it might no longer exist, leaving behind only automated systems carrying out missions designed by minds that perished before our sun was born. This raises the chilling possibility that we might not be dealing with active alien intervention, but rather with the vestiges of some ancient civilization, autonomous systems executing programmed directives across deep time, perhaps no longer serving any living intelligence, but continuing to fulfill their original mission parameters with mechanical precision. Of course, and this bears constant repetition, none of this speculative narrative is supported by current observations of 3I Atlas. Every observation, every spectral analysis, every visual capture consistently reinforces the concept of a naturally occurring comet. The celestial body's conduct precisely mirrors what astronomical models forecast for an interstellar comet. Its molecular composition, while uncommon, falls within the spectrum of natural planetary processes. Its flight path adheres to the fundamental principles of physics, requiring no extraordinary justifications. The merit of this hypothetical exploration resides not in its likelihood, but in its demonstration of how rapidly our cosmic outlook could transform should our foundational assumptions prove insufficient. It serves as a potent reminder that the universe has previously astonished us and will undoubtedly continue to do so. Furthermore, it underscores the crucial need to maintain both a healthy sense of skepticism toward extraordinary assertions and an open mind toward possibilities that transcend our present comprehension. As we proceed on this venture into increasingly speculative realms, it is vital to remember that we are charting the expanse of potential rather than the solid ground of established truths. The real 3I Atlas remains a captivating natural phenomenon, ancient, swift, chemically peculiar, yet fundamentally understandable within our current scientific paradigm. Whether this comprehension will ultimately suffice remains an open inquiry, one destined to be resolved by future observations with the unyielding clarity that only empirical evidence can provide. Part 8. Alarms from the Great Filter. The notion of the Great Filter arises from one of the most significant questions confronting any advanced civilization. If the universe were teeming with intelligent life, why do we find no evidence of its presence? This philosophical quandary, first articulated by physicist Enrico Fermi during the 1950s, has fueled decades of contemplation regarding the obstacles that might impede life's emergence, development, or enduring existence long enough to populate the galaxy. Within our speculative examination of 3I Atlas, we must grapple with the possibility that this ancient traveller might carry messages from intelligences that confronted their own insurmountable hurdles. The Great Filter hypothesis posits that at some point in the vast continuum of evolutionary progression, from basic chemistry to a starfaring society, there exists a phase so improbable, so arduous, or so perilous that nearly all attempts to surmount it result in failure. This barrier could manifest early in the sequence, perhaps during the transformation from inanimate matter to self-sustaining systems. Alternatively, it might emerge later when societies develop technologies potent enough to annihilate themselves more rapidly than they can acquire the wisdom to wield them responsibly. Should we allow ourselves to envision 3i Atlas as a product of deliberate engineering rather than natural occurrence, we must immediately confront the destiny of its creators. The object's apparent antiquity, potentially spanning billions of years, situates its origin in the deep past of our galaxy, a time when stellar populations, elemental abundances, and cosmic circumstances differed significantly from present-day conditions. If this ancient interloper were indeed artificial, did the civilization responsible for its creation endure long enough to witness its arrival in our solar system? The temporal scales involved are almost beyond human grasp. Human civilization, from its earliest agricultural settlements to our current era of space exploration, spans approximately 10,000 years. Recorded history encompasses roughly 5,000 years. Our technologically advanced civilization has existed for mere centuries. Yet 3i Atlas, if artificial, would represent a technological artifact operational for millions of times longer than our entire history as a civilization. This scenario prompts profound contemplation on the longevity of technology versus the persistence of biological life. Perhaps the most unsettling prospect is that we might be encountering probes that endure long after their creators have vanished. Cosmic messages in bottles drifting through the galaxy, conveying information from civilizations that surmounted the technical challenges of interstellar communication, but ultimately succumbed to other manifestations of the Great Filter. Consider the engineering feats required to construct technology capable of functioning across such vast temporal expanses. Our most enduring human creations, such as the pyramids, ancient stone structures, and certain radioactive elements, operate on timescales ranging from thousands to millions of years. However, maintaining intricate electronic systems, propulsion mechanisms, and artificial intelligence over billions of years would necessitate engineering principles that are currently difficult to conceptualize. It would demand material science capable of producing components surpassing the durability of diamond, energy systems that function for longer periods than most stars burn, and software architectures designed to adapt and self-repair across geological epochs. The success of such engineering would paradoxically imply that its originators possessed extraordinary technological capabilities. Any civilization capable of launching interstellar missions lasting billions of years would have overcome numerous technical challenges that we have yet to even contemplate. They would possess an understanding of materials at the atomic level, energy generation, and storage on cosmic scales, and information processing across deep time. Such accomplishments would seemingly offer protection against many potential Great Filter scenarios. Yet, if 3i Atlas were indeed their creation, and if it represents the sole evidence of their existence, what Great Filter might have claimed them despite their technological prowess? The possibilities are sobering to contemplate. Perhaps they succumbed to resource depletion on a galactic scale, expanding so rapidly that they exhausted the energy and materials essential for their civilization's survival. It is conceivable that they encountered other intelligences that proved hostile, igniting conflicts that led to the destruction of both aggressor and defender. More disquieting still, they might have fallen victim to intrinsic contradictions within advanced technological civilizations. The very capabilities that enabled them to engineer interstellar probes could have facilitated forms of warfare, ecological devastation, or societal collapse that proved unmanageable. History offers numerous instances of civilizations that advanced technologically more rapidly, then they develop the wisdom to employ these technologies safely. Our own species currently faces several such dilemmas. Alternatively, the Great Filter might not involve catastrophic annihilation, but rather evolutionary transcendence. It is possible that highly advanced civilizations inevitably transform themselves in ways that render them unrecognizable or undetectable to emerging species like our own. They might upload their consciousnesses into quantum computing systems, merge so completely with their technology that the distinction between intelligence and artifact vanishes, or ascend to higher dimensions of existence that remain imperceptible to our current sensory apparatus. The cosmic perspective required to contemplate such scenarios can induce a profound sense of vertigo. Our galaxy contains approximately 400 billion stars, many of which ignited billions of years before our Sun. If even a minuscule fraction of those stellar systems gave rise to technological civilizations, the galaxy should have been thoroughly explored and settled multiple times over. The absence of an obvious alien presence, a phenomenon astronomers refer to as the Great Silence, demands an explanation. Current SETI, Search for Extraterrestrial Intelligence, practices reflect the uncertainty generated by these questions. Most searches prioritize passive listening over active transmission, as revealing our presence before we fully comprehend the galactic environment might be premature or perilous. The discovery of artificial signatures within 3i Atlas would instantaneously transform these cautious investigations into urgent strategic considerations. The observational safeguards we have implemented throughout this inquiry become even more critical when considering Great Filter scenarios. Current data pertaining to 3i Atlas continues to support natural explanations for its behaviour, composition, and trajectory. Speculation regarding artificial origins and civilizational demise remains precisely that: speculation, lacking evidentiary support and maintained solely as an intellectual exercise. Nevertheless, the questions prompted by such speculation are not purely academic. They compel us to confront fundamental issues concerning technological advancement, civilizational sustainability, and the long-term prospects of our own species. If advanced civilizations routinely encounter barriers that prevent their survival across cosmic timescales, what lessons might this offer humanity's current trajectory? The concept of the Great Filter serves as both a cautionary tale and a source of inspiration. It warns that technological capability alone may not guarantee survival, and that progress brings new forms of risk alongside opportunity. However, it also inspires us to thoughtfully consider how we manage our own development, how we balance exploration with prudence, and how we might engineer solutions that prove more enduring than the civilizations that conceive them. In our speculative narrative, 3i Atlas transforms into a cosmic artifact of archaeological significance. Physical evidence of an intelligence that achieved remarkable technical feats, but ultimately fell victim to forces we can only surmise. The probe continues its ancient journey through deep time, carrying messages from minds that solved the complexities of interstellar engineering, but failed to surmount the more profound challenge of sustained existence. This scenario would place humanity in the position of cosmic inheritors, discovering technology from predecessors who navigated paths we're only beginning to tread. The responsibility would be immense, learning from their accomplishments while diligently avoiding whatever Great Filter claimed their civilization. The stakes would involve nothing less than the ultimate survival of our species and our potential to contribute something meaningful to the cosmic dialogue. However, these remain philosophical contemplations rather than scientific conclusions. The real 3i Atlas continues to behave precisely as natural comets are expected to, following trajectories dictated by gravity and physics rather than intelligence and intent. Whether this understanding will prove sufficient will ultimately be determined by observation and evidence. As we venture further into speculative domains, the imperative to maintain a clear distinction from verifiable reality becomes increasingly important. The universe has already proven sufficiently wondrous through natural processes alone. From the intricacies of quantum mechanics to the enigma of dark energy, and the vast cosmic web of large-scale structure, the introduction of artificial intelligence to this already extraordinary reality might prove unnecessary for achieving the sense of awe and cosmic perspective that fuels all scientific inquiry. Part 9. Fermi's Whisper. Where is everybody? The question reverberates through every astronomical discovery, lurking behind every search for extraterrestrial intelligence, haunting every moment we peer into the cosmic void and find only silence. Enrico Fermi posed it during a casual lunch discussion in 1950, but its implications have only deepened as our understanding of the universe has expanded. If the galaxy is indeed teeming with intelligent civilizations, if the cosmos presents countless opportunities for life to arise and evolve, then where is everyone? This Fermi paradox takes on novel dimensions when we consider interstellar objects such as 3I Atlas. Each visitor from beyond our solar system represents a natural experiment in the distribution of matter throughout the galaxy, a sample of the materials and processes occurring around other stars. In theory, these wandering ambassadors should eventually reveal signatures of technological civilization, engineered materials, artificial isotope ratios, structured objects betraying intelligent design. Yet, thus far, all confirmed interstellar visitors have appeared entirely natural. This absence might be conveying something profound about the nature of advanced civilization and its relationship with interstellar space. Perhaps truly advanced societies favour what we might term silent emissaries. If they dispatch probes at all, these craft are designed to be indistinguishable from natural phenomena. In such a case, the very sophistication of alien technology would render it invisible to our current detection methods, which remain calibrated to identify overtly artificial signatures. However, this immediately raises questions about what those signatures would entail. If 3I Atlas were indeed some form of concealed probe, what observational evidence would ultimately confirm its true nature? The answer brings us back to the fundamental distinction between natural and artificial phenomena in space, a boundary that may prove more subtle and complex than our current understanding suggests. Narrowband radio emissions would represent the most unambiguous technological signature. Natural processes in space generate radio noise across broad frequency ranges, but artificial transmissions typically concentrate their energy within narrow spectral lines that stand out clearly against the cosmic background. The search for extraterrestrial intelligence has, for decades, focused on detecting precisely such signals, operating under the assumption that any civilization capable of interstellar communication would produce detectable electromagnetic signatures. To date, 3I Atlas has remained radio silent, emitting only the natural electromagnetic signatures expected from sublimating cometary material interacting with the solar wind and magnetic fields. Dedicated SETI observations have failed to detect any coherent signals, modulated transmissions or artificial patterns within its electromagnetic output. This silence aligns perfectly with the natural comet hypothesis, but cannot definitively rule out more sophisticated forms of concealment technology. Unnatural thermal profiles could offer another diagnostic tool. Natural objects in space achieve thermal equilibrium with their surroundings, according to well-understood physical principles. They absorb solar radiation, re-radiate energy in the infrared spectrum, and maintain surface temperatures determined by their distance from the sun, their composition, and their thermal properties. Artificial objects might exhibit temperature distributions that deviate from these natural patterns, potentially due to internal heat sources, asymmetric heating, or thermal management systems indicating active control. Current infrared observations of 3I Atlas display thermal signatures consistent with solar heating of natural cometary materials. Its surface temperature increases as it approaches the sun, following the inverse square law that governs solar energy distribution. The spatial distribution of heat across its surface appears random, shaped by topographic features and compositional variations, rather than by designed thermal management systems. Controlled maneuvers would represent perhaps the most conclusive evidence of artificial origin. Natural objects in space follow trajectories dictated solely by gravitational forces and occasional thrust from outgassing materials. These non-gravitational accelerations are typically minor, random in direction, and closely correlated with indicators of cometary activity, such as coma brightness and gas production rates. Artificial probes, conversely, might exhibit controlled course corrections, intentional velocity changes, or trajectory modifications designed to achieve specific mission objectives. Such maneuvers would need to be carefully distinguished from the chaotic forces generated by asymmetric outgassing, but persistent patterns of controlled motion would eventually become apparent through precise astrometric measurements. 3I Atlas has shown no indication of controlled maneuvers. Its trajectory follows the smooth hyperbolic arc predicted by gravitational calculations, with only minor perturbations that correspond precisely to the expected effects of solar radiation pressure and outgassing forces. If it possesses propulsion capabilities, they remain either inactive or too subtle to detect with current observational precision. The natural explanation for interstellar objects like 3I Atlas aligns well with theoretical expectations regarding planetary system formation. Computer simulations suggest that all stellar systems should eject substantial quantities of rocky and icy debris during their early evolutionary stages. When gravitational interactions between planets scatter smaller bodies onto interstellar trajectories, the galaxy should be populated with such nomads, planetesimals that began forming around other stars but were flung into the void before they could develop into full-fledged worlds. From this perspective, the steady influx of interstellar visitors we've begun to detect represents precisely what astronomical theory predicts. Oumuamua, 2I Borisov, and 3I 2019 Q4, 2I Borisov, are the vanguard of a much larger population that future surveys will reveal. The Vera C. Rubin Observatory, scheduled to commence operations later this decade, is expected to detect interstellar objects at a rate of several per year, transforming them from rare curiosities into routine astronomical occurrences. This statistical argument offers one potential resolution to the Fermi paradox as it applies to interstellar objects. If naturally ejected planetesimals vastly outnumber any artificial probes, then the artificial signatures we seek might be obscured within a background of natural wanderers. Detecting alien technology would necessitate distinguishing a few engineered objects from thousands or millions of natural ones, a problem of extraordinary difficulty, akin to finding a needle in a cosmic haystack. The chemical diversity revealed by 3I Atlas adds another layer to this statistical picture. Its composition, rich in carbon dioxide, expands the known range of volatile ratios in interstellar objects, suggesting that different stellar environments produce distinct types of ejected materials. As our sample size grows, we may discover that the chemical signatures we initially interpreted as unusual or potentially artificial actually represent the natural variability of planetary formation processes across the galaxy. Survey biases complicate our interpretation of the interstellar objects detected thus far. Ground-based telescopes and space-based surveys preferentially identify objects approaching from specific directions, possessing particular brightness characteristics and following certain orbital geometries. The 3 confirmed interstellar visitors may not be representative of the broader population, much like the first exoplanets discovered. Predominantly hot Jupiters in close orbits around their stars did not reflect the full diversity of planetary systems. 3I Atlas's arrival from the southern skies surprised some astronomers who anticipated interstellar objects would predominantly arrive from the direction of the galaxy's rotation. This unexpected trajectory suggests either that our models of interstellar object distribution remain incomplete, or that individual objects can be scattered by gravitational encounters in ways that mask their original motion patterns. Future astronomical capabilities will dramatically enhance our capacity to address these questions, The Vera C. Rubin Observatory's Legacy Survey of Space and Time will detect hundreds of interstellar objects over its planned 10-year mission, providing statistical samples large enough to test theoretical predictions regarding their origins, compositions, and trajectories. Space-based infrared telescopes will characterize their thermal properties and chemical compositions with unprecedented precision. These expanding datasets will either confirm that interstellar objects conform to natural distributions predicted by planetary formation theory, or reveal anomalies that necessitate more unconventional explanations. If alien probes exist among the wandering population, larger samples and improved instrumentation will eventually expose their artificial nature through subtle but consistent deviations from natural behavioral patterns. The philosophical implications of continued silence should not be underestimated. Every natural celestial body we examine provides further validation for the theory that advanced intelligence capable of cosmic construction either does not exist, remains hidden from our current observation methods, or deliberately avoids displaying easily identifiable signs. The growing realization of our isolation in the cosmos is amplified with each confirmed non-terrestrial object encountered. However, the absence of proof does not equate to proof of absence, particularly given our restricted detection capabilities and limited sample size. The universe may yet unveil marvels that redefine our conceptions of intelligence, technological prowess, and their manifestations in space. Object 3. Atlas, whether it be of natural or artificial origin, represents another piece of evidence in humanity's ongoing quest to ascertain its position within the celestial community. As our exploration ventures into increasingly speculative territories, maintaining a clear distinction between observation and imagination becomes paramount. The actual cosmos, illuminated through diligent observation and meticulous analysis, has already revealed itself as sufficiently peculiar and awe-inspiring without the need for fabricated embellishments. Whether this curious reality encompasses other forms of intelligence remains an unresolved query, one that future discoveries will undoubtedly settle with the definitive authority of empirical data. Part 10. A Cinematic Fable. The Silent Infiltration via Microscopic Envoys. Now, we venture into the domain of pure cinematic fantasy, where the lines between plausible science fiction and observable reality blur into scenarios that would challenge our fundamental understanding of life, intelligence, and the universe itself. What follows represents the absolute fringe of theoretical possibility, concepts so far-reaching that they necessitate the suspension of numerous scientific principles, yet retain enough connection to established physics to spark our imagination. Envision this narrative. 3 Atlas is not merely a probe or a standard spacecraft, but rather a sophisticated delivery mechanism for something far more subtle and insidious. Concealed within its icy structure lie microscopic apparatuses, or perhaps even artificially designed biological entities. Let us refer to them as microseeds, in a dormant state, awaiting activation by specific environmental cues. These could be nanotechnological constructs engineered to endure the arduous conditions of interstellar space for eons, or they might embody a form of pangalactic life that propagates between star systems through precisely this method. This concept is not entirely without precedent in scientific conjecture. The hypothesis of panspermia, while debated and far from substantiated, posits that life itself could disperse throughout the galaxy via comets, asteroids, and other cosmic wanderers. Certain researchers have suggested that robust microorganisms could survive the radiation, vacuum, and extreme cold of space for millions, even billions of years, thereby seeding new worlds upon encountering suitable conditions. However, our speculative scenario transcends mere passive panspermia. These hypothetical microseeds would represent meticulously engineered systems, designed not only to withstand interstellar transit, but also to remain dormant until particular activation criteria are met. They might react to the electromagnetic signatures of technologically advanced civilizations, becoming active only upon detecting radio transmissions, industrial pollutants, or other indicators of intelligent presence. Alternatively, they could be triggered by solar radiation patterns, awakening as their host object approaches stars of specific spectral types. The engineering hurdles involved would be immeasurably immense, far beyond our current comprehension. These microscopic devices would need to maintain their structural integrity across timescales spanning billions of years, enduring cosmic radiation, impacts from interstellar dust, and the extreme temperature fluctuations of deep space. They would necessitate power sources that outlast the lifespans of most stars, information storage systems impervious to geological degradation, and manufacturing capabilities capable of assembling complex technologies from raw materials found on alien planets. Yet, if such technology were attainable, its strategic implications would be profoundly alarming. A single interstellar object like 3 Atlas could harbour billions, or even trillions, of microscopic seeds, each possessing the potential to establish a foothold on any world it eventually reaches. The infiltration, if it could be termed such, would be silent, patient, and virtually imperceptible until the activation phase commenced. The activation scenario within our speculative narrative might unfold centuries or millennia after 3 Atlas traverses our solar system. Perhaps the microseeds are programmed to activate when Earth's technology reaches certain thresholds, when we ourselves achieve interstellar travel, when our population attains specific densities, or when our industrial activities produce particular atmospheric markers. This temporal delay would serve multiple strategic objectives, allowing for detailed reconnaissance of human civilization, ensuring activation occurs when humanity is sufficiently developed to fulfill whatever purpose the seeds are intended for, and preserving plausible deniability regarding the connection between the initial deployment and the eventual activation. However, here is where stark reality intrudes upon this speculative fantasy. The extreme conditions that 3 Atlas has endured throughout its interstellar journey would pose nearly insurmountable challenges to any form of complex technology or biology. Cosmic radiation alone would systematically degrade molecular structures over timescales measured in millions of years, let alone the billions of years suggested by the object's apparent age. Even the most radiation-resistant organisms known on Earth would succumb to such prolonged exposure. The chaotic outgassing that renders 3 Atlas visible as a comet would introduce additional perils for any microscopic hitchhikers. As volatile ices sublimate and expand into the vacuum of space, they would carry along dust particles and any other minute materials embedded within the nucleus. The ferocity of this process, occurring each time the object approaches a star during its billion-year voyage, would likely obliterate delicate structures and disperse any microscopic components across immense distances. The extreme dilution factors involved also argue against the practical efficacy of such a delivery mechanism. Even if 3 Atlas contained billions of microseeds, the vast majority would be expelled into space during outgassing events, lost to the vacuum between worlds. The few that might somehow reach Earth's proximity would face further dilution within our planet's atmosphere and biosphere, rendering it virtually impossible for any significant concentration to accumulate in any specific location. The closest approach distance of 1.88 astronomical units offers another reality check on this speculative scenario. 3 Atlas will pass Earth at approximately twice the distance of Mars, with no possibility of direct material exchange. Any microseeds would need to survive not only the billion-year interstellar journey and the violent outgassing process, but also the subsequent voyage across hundreds of millions of kilometers of interplanetary space to reach our world. Current planetary protection protocols, developed by space agencies to prevent contamination of both Earth and other celestial bodies, provide frameworks for how we might respond to hypothetical material capture from objects like 3 Atlas. These procedures encompass stringent containment measures, analysis in specialized biosafety laboratories, and careful evaluation of any biological or technological signatures. However, Such protocols presume direct sample return missions, not the passive capture of microscopic materials dispersed across vast distances. The challenges associated with monitoring for such a speculative threat would be immense. How does one search for microscopic devices or organisms that might be designed to remain dormant for centuries? What signatures would they produce that could be distinguished from natural microorganisms, space dust, or terrestrial contamination? The task would be akin to searching for needles within a haystack the size of our entire solar system. Long baseline radar systems, the kind used to track space debris and potentially hazardous asteroids, would be unlikely to detect objects as small as microscopic seeds. Optical surveys fare even worse when dealing with particles measured in micrometers rather than kilometers. Even if such monitoring were theoretically feasible, the resource commitment would be staggering, demanding constant vigilance across the entire spatial volume surrounding Earth. This brings us to the fundamental weakness of our speculative silent invasion scenario. It contravenes core principles of engineering efficiency. Any civilization possessing the capability to design billion-year interstellar delivery systems would presumably have access to far more direct and reliable methods of achieving whatever objectives such an invasion might entail. The complexity, uncertainty, and temporal delays inherent in microscopic seed distribution render it an implausibly inefficient approach when compared to alternatives such as directed energy transmission, conventional spacecraft, or even simple radio communication. The scenario does serve one valuable purpose in our speculative exploration. It illustrates how our imaginations can outpace physical possibility when confronted with cosmic enigmas. The same sense of wonder and cosmic apprehension that fuels legitimate scientific inquiry can also engender fears that exceed the bounds of plausible reality. Distinguishing between prudent caution and unfounded speculation becomes critical when dealing with genuinely unprecedented phenomena. Our documentary treatment of such scenarios necessitates clear and prominent disclaimers regarding their speculative nature. Viewers must understand that we're exploring the landscape of imagination rather than the territory of established fact. These thought experiments can be instrumental in broadening our thinking about possibilities, but they should not be mistaken for probable or even plausible realities. The counter-narrative remains straightforward and compelling. The most parsimonious explanation for 3 Atlas's behaviour is that cometary dust behaves precisely as cometary dust does. The object exhibits all the characteristics we anticipate from natural cometary material: appropriate spectroscopic signatures, predictable thermal behaviour, and outgassing patterns that precisely correlate with solar heating. No additional hypotheses are required to account for its observed properties. As we approach the conclusion of our speculative journey into increasingly dramatic scenarios, it is worth reflecting on what these thought experiments reveal about human psychology and our relationship with cosmic uncertainty. Our inclination to envision exotic explanations for unusual phenomena reflects both our creativity and our apprehension regarding our place in a universe that frequently appears indifferent to our existence. The actual 3 Atlas, the observed, measured and analysed object hurtling through our solar system at tremendous velocity, remains remarkable enough without the need for fanciful additions to its narrative. It is an ancient traveller from another stellar system, bearing chemical traces of alien environments, offering us a brief glimpse into the deep history and vast expanse of our galaxy. That is extraordinary enough to inspire wonder and scientific investigation without invoking invasion scenarios or hidden technologies. However, the exercise of exploring such possibilities serves its own purpose in our ongoing endeavour to comprehend our cosmic context. By pushing speculation to its limits, we gain a better appreciation for both the genuine mysteries that surround us and the constraints that physics and evidence impose upon reasonable explanations. The universe has proven to be strange enough through natural processes alone, perhaps stranger than our imaginations can readily grasp, but strange in ways that ultimately yield to patient observation and careful analysis. Part 11. If 3 Atlas were a visitor, how would we respond? The response thus far has been a testament to the finest aspects of human scientific collaboration, a choreographed ballet of telescopes, institutions, and individual researchers working in concert to extract maximum knowledge from a fleeting opportunity. Within hours of its initial discovery by the Atlas survey on the 1st of July, 2025, a global network of observatories had initiated coordinated action, demonstrating how modern astronomy functions as a truly international enterprise. The immediate reaction adhered to protocols developed over decades of asteroid and comet discoveries. The Minor Planets Center at the Harvard-Smithsonian Astrophysical Observatory served as the central clearinghouse for astrometric observations, compiling positional measurements from observatories worldwide and refining the object's orbital elements with each successive data point. The European Space Agency's Space Situational Awareness Programme contributed its tracking capabilities, while NASA's Planetary Defense Coordination Office assessed any potential Earth impact risk, a calculation that swiftly ruled out any collision threat. However, 3 Atlas's interstellar nature elevated the response beyond routine asteroid tracking procedures. The Hubble Space Telescope was granted priority target of opportunity scheduling, interrupting previously planned observations to image this unprecedented visitor. The James Webb Space Telescope followed suit, dedicating precious observation time to spectroscopic analysis of the object's unusual carbon dioxide-dominated coma. Ground-based observatories, from Chile's Atacama Desert to Hawaii's Mauna Kea, provided complementary observations across the electromagnetic spectrum. This coordinated response exemplifies the astronomical community's evolution in handling rapid response scenarios. Unlike the early days of astronomy, when discoveries might remain confined to individual researchers' notebooks for months or years, modern astronomical surveys automatically share their findings through established networks. The International Astronomical Union's Central Bureau for Astronomical Telegrams, despite its somewhat antiquated name, provides near-instantaneous notification of significant discoveries to researchers globally. The information flow surrounding 3.2 Atlas has been remarkably transparent. NASA's official website offers regular updates on observational results, complete with detailed technical information and accessible explanations for a general audience. The European Space Agency has published similar updates, emphasizing the collaborative nature of the observation campaign. Popular astronomy publications such as Sky and Telescope magazine have provided in-depth technical coverage alongside practical observing guides for amateur astronomers, hoping to catch a glimpse of this interstellar visitor through their own telescopes. But imagine, for a moment, if our earlier speculative scenarios proved accurate. Suppose future observations began to reveal signatures that could not be explained by natural processes, coherent radio transmissions, controlled trajectory adjustments, or the deployment of secondary objects throughout our solar system. How would our institutions and procedures scale up to address what might become the most profound discovery in human history? The existing framework offers some guidance. The International Astronomical Union has protocols for verifying extraordinary claims, requiring independent confirmation from multiple observatories before accepting findings that challenge established scientific understanding. The SETI Institute has developed communication protocols for potential first contact scenarios, including guidelines for information sharing, public notification, and international cooperation. Space agencies maintain planetary protection procedures designed to prevent the contamination of Earth by alien microorganisms or theoretically more exotic life forms. Yet, none of these existing frameworks were designed to handle the discovery of active alien technology operating within our solar system. The scale of coordination required would dwarf anything previously attempted in scientific research. Questions of jurisdiction would immediately arise. Which international body would hold authority over first contact protocols? How would response be coordinated among nations that might view the discovery as either an opportunity or a threat? What would transpire when scientific curiosity clashed with security concerns? The political ramifications would be staggering. Any confirmation of alien technology would instantly become a matter of national security for every major power on Earth. Military establishments, which currently view space primarily as a domain for surveillance and communication, would suddenly confront the reality of non-human intelligence with potentially superior technological capabilities. The balance between transparency and security, which has generally favoured openness in astronomical research, might shift dramatically toward classification and restricted access. The technical challenges of responding to confirmed alien presence would test every facet of our spacefaring capabilities. Current spacecraft require years to reach the outer solar system, where 3.2 Atlas is currently located, and decades to achieve interstellar velocities. If the object were indeed artificial and time-sensitive communication were desired, our only practical option might be radio transmission. Assuming the alien technology utilized communication protocols we could recognize or decode, the absence of any realistic interception capability highlights humanity's current limitations in space technology. Despite decades of impressive achievements in robotic exploration, we remain firmly confined to our immediate solar neighborhood, with transit times measured in years rather than months. Any meaningful interaction with fast-moving interstellar objects would necessitate technological capabilities that we do not currently possess and could not develop quickly enough to be relevant for objects like 3 Atlas. Public communication strategies would face unprecedented challenges. How does one announce the discovery of alien intelligence without triggering widespread panic or social disruption? The careful, measured tone that space agencies have adopted for 3.2 Atlas announcements, emphasizing scientific interest while minimizing sensational interpretations, would need to evolve rapidly to handle far more extraordinary claims while maintaining credibility and public trust. The lessons learned from previous false alarms would become crucial. The WOW signal, detected by SETI researchers in 1977, generated immense initial excitement, but ultimately proved to be a one-time event that could not be independently confirmed or replicated. More recently, the unusual properties of Oumuamua led to brief speculation about an artificial origin before more conventional explanations emerged. These experiences have taught scientists and science communicators the importance of distinguishing between intriguing observations and definitive conclusions. Media management would become a critical component of any response to confirmed alien technology. The 24-hour news cycle's appetite for dramatic developments could easily overwhelm careful scientific analysis with speculation and misinformation. Social media platforms would face immense challenges distinguishing between legitimate updates from verified sources and the inevitable deluge of conspiracy theories, hoaxes, and misinterpretations that would accompany such a momentous discovery. The economic implications alone would necessitate careful response planning. Financial markets would likely experience extreme volatility as investors attempt to factor in the ramifications of confirmed alien technology. Entire sectors of the economy could face profound questions about their future if extraterrestrial science provided groundbreaking solutions to present-day energy, transport, or manufacturing methods. The stability of the world's financial system might hinge on how effectively organizations could navigate the shift from conjecture to validated facts. Educational bodies would experience immediate pressure to redefine their research agendas and core beliefs regarding humanity's position in the cosmos. The ramifications would extend across every academic field, from the study of celestial bodies and the fundamental laws of nature to the examination of human societies, spiritual beliefs, and governance. Institutions that have dedicated centuries to mastering the understanding of earthly phenomena would suddenly need to integrate non-human intelligence into their perception of reality. The limited time frame dictated by the high-velocity trajectory of 3 Atlas lends urgency to any hypothetical reaction strategy. Unlike the slow progression of most cosmic events, interstellar travelers arrive and depart on schedules governed by the laws of physics, not by human convenience. Any substantial response would need to be formulated and enacted within mere months, not years. forcing conventional decision-making procedures into timeframes that strain organisational capacities. Nevertheless, the actual response to 3i Atlas has displayed noteworthy efficiency within these constraints. The international community of astronomers identified the object, confirmed its non-terrestrial origin, synchronized observations across various wavelengths, and commenced in-depth analysis within weeks of its initial detection. This performance indicates that existing structures and protocols, though not flawless, offer a robust foundation for managing even unprecedented discoveries. The theoretical framework for responding to confirmed extraterrestrial contact has been developing for decades, thanks to the efforts of SETI researchers, astrobiologists, and international legal experts. While these preparations may not cover every conceivable scenario of actual contact, they provide foundational elements for the types of decisions that would need to be made swiftly under extraordinary circumstances. Perhaps most significantly, the reaction to 3i Atlas has prioritized inquisitiveness over apprehension, scientific inquiry over speculation, and global collaboration over competitive secrecy. These guiding principles, demonstrated through the open dissemination of observational data and the cooperative nature of the research effort, represent humanity's most effective approach to cosmic enigmas, irrespective of their ultimate explanation. The real-world reaction confirms our possession of both the technological means and the organisational frameworks necessary to effectively study extraordinary phenomena. Whether these same capacities would prove sufficient for genuine first contact remains an open query, but the coordinated professional response to 3 Atlas offers a basis for optimism regarding our species' ability to handle even more remarkable celestial encounters. As we move from pondering alien contact towards more grounded discussions of cosmic perspective and scientific methodology, the response to 3i Atlas serves as an instructive example of how contemporary civilization confronts the unknown. The synergy of technological prowess, institutional coordination, and intellectual curiosity that has defined the 3 Atlas investigation provides a blueprint for engaging with mysteries that may prove even more transformative to our understanding of existence. Part 12. Containment or Curiosity. The dilemma of balancing scientific curiosity against potential hazards epitomizes one of the most fundamental conflicts in human exploration. This is the same conflict that has propelled us to traverse oceans, ascend mountains, and journey into space, despite the inherent dangers. In the instance of 3i Atlas, this equilibrium has decisively shifted towards curiosity, and rightly so. The object's path and characteristics render most imagined containment strategies unfeasible, while simultaneously maximizing opportunities for scientific revelation. Current planetary protection guidelines, refined through decades of space exploration experience, offer frameworks for considering contamination risks in both directions, safeguarding Earth from alien microorganisms and protecting other celestial bodies from terrestrial life. However, these protocols were primarily devised for missions involving direct sample return and close spacecraft proximity, not for objects that traverse our solar system at safe distances without exhibiting any apparent signs of biological activity. The fundamental structure of planetary protection is built upon risk assessment and proportionate response. When NASA's Perseverance rover collected samples from Mars, extensive precautions were planned for their eventual return to ensure that any hypothetical Martian microorganisms would not escape into Earth's biosphere. Similarly, spacecraft destined for potentially habitable moons such as Europa undergo rigorous sterilization processes to prevent forward contamination of alien environments. 3IE Atlas presents a fundamentally distinct situation. Its closest approach distance of 1.8 astronomical units, approximately 270 million kilometers, precludes any possibility of direct material transfer with Earth. No spacecraft interception is planned or even practically achievable, given current technological limitations and the object's extreme velocity. The question of containment becomes largely theoretical when the object in question will never come sufficiently close to be contained. This considerable distance has facilitated a remarkably open approach to data sharing and scientific collaboration. Images from the Hubble Space Telescope, spectroscopic data from the James Webb Telescope, and ground-based observations have been made accessible through standard astronomical archives, enabling researchers globally to analyze identical datasets and validate each other's findings. This transparency exemplifies the scientific method at its finest. Multiple independent investigators examining identical evidence and arriving at congruent conclusions regarding the object's natural origin. The culture of open archives that has emerged around major space telescopes warrants particular commendation. The Minkowski Archive for Space Telescopes provides access to Hubble and Webb observations for any researcher with internet connectivity, democratizing astronomy in ways unimaginable just a few decades ago. The European Southern Observatory maintains comparable archives for ground-based observations, while amateur astronomers contribute their own imagery and light curves through various citizen science platforms. This openness stands in stark contrast to the secrecy that might characterize military or intelligence responses to potential extraterrestrial contact. The scientific community's default inclination towards transparency reflects both practical imperatives, peer review necessitates data sharing, and philosophical commitments to the universal nature of scientific knowledge. The 3 Atlas investigation demonstrates how these principles operate even when studying phenomena that, in principle, could represent our initial encounter with alien intelligence. The informational landscape surrounding 3 Atlas also illustrates both the advantages and challenges of instantaneous global communication. Legitimate scientific findings propagate rapidly through professional networks, facilitating near real-time collaboration among researchers on different continents. However, the same communication channels that enable productive scientific exchange also transmit misinformation, speculation, and sensationalize misinterpretations that can distort public understanding. Patterns of misinformation surrounding astronomical discoveries have become increasingly sophisticated and widespread. Social media algorithms that prioritize engagement over accuracy tend to amplify dramatic claims and conspiracy theories at the expense of measured scientific analysis. The challenge of differentiating between legitimate scientific uncertainty, the kind that fuels productive research, and unfounded conjecture has become critical for maintaining rational public discourse about cosmic discoveries. The case of 3 Atlas provides a useful illustration of how these information dynamics function. Mainstream scientific sources have consistently highlighted both the object's unusual characteristics and its natural origin, acknowledging uncertainty while avoiding unsupported speculation. Less reputable sources have sometimes exaggerated preliminary findings, conflated conjecture with established fact, or promoted conspiracy theories about government cover-ups of extraterrestrial contact. Visual communication plays a pivotal role in these information dynamics. Images of 3 Atlas captured by Hubble and Webb, processed and enhanced to reveal scientific details, can appear dramatic and otherworldly to the general public. The challenge lies in presenting these images within contexts that emphasize their scientific rather than sensational significance, illustrating how observed features confirm cometary behavior rather than suggesting alien technology. The question of containment versus curiosity takes on different dimensions when we consider not physical containment, but informational containment. Should certain types of astronomical discoveries be subject to classification or restricted dissemination? The scientific community has generally responded negatively, arguing that the benefits of open collaboration outweigh hypothetical security risks posed by publicly accessible astronomical data. This stance reflects both practical and philosophical considerations. Practically, astronomy thrives most effectively as a global endeavour where researchers share data, validate each other's findings, and build upon collective knowledge. Philosophically, the perspective from space has historically served to unite rather than divide humanity, emphasizing our shared cosmic heritage over terrestrial conflicts. The precedent set by previous potentially anomalous astronomical discoveries supports continued openness. The pulsar discoveries of the 1960s, briefly labelled LGM for Little Green Men, ultimately illuminated new physics rather than alien intelligence. The WOW signal detected by SETI researchers remains unexplained but has been thoroughly documented and analysed in public forums. Even Oumuamua's unusual properties were studied through transparent international collaboration rather than classified research programs. Citizen science contributions to 3I Atlas observations exemplify another facet of the curiosity over containment approach. Amateur astronomers equipped with modest instruments have captured images and light curves that complement professional observations, adding to the body of information that will ultimately inform our scientific understanding. This democratization of astronomical research would be impossible under containment-focused policies, but has proven invaluable for advancing genuine scientific knowledge. The FEREX mission's potential role in mapping 3 Atlas's extended carbon dioxide coma illustrates how next-generation surveys will further enhance our capacity to study such objects. Wide-field infrared missions like SPHERE-X can complement the detailed spectroscopy provided by Webb, creating comprehensive portraits of interstellar visitors that no single instrument could achieve alone. Looking ahead, the Vera C. Rubin Observatory promises to revolutionize our understanding of interstellar objects by detecting hundreds of such visitors over its planned operational lifespan. This statistical approach will either confirm that objects like 3 Atlas represent natural phenomena following predictable distributions, or reveal anomalies that necessitate more unconventional explanations. The institutional approach to studying these future discoveries has been shaped by the experience with 3 Atlas. The rapid coordination among observatories, the transparent data sharing protocols, and the emphasis on international collaboration provide a model for handling even more unusual discoveries. Should genuinely anomalous objects eventually be detected, the scientific community appears well prepared to study them through the same open, collaborative methods that have characterized the 3 Atlas investigation. The balance between skepticism and openness that has defined professional astronomical responses to 3 Atlas offers another template for future discoveries. Healthy scientific skepticism demands extraordinary evidence for extraordinary claims, but it also requires remaining receptive to possibilities that transcend current understanding. The 3 Atlas investigation has demonstrated how to maintain this balance, acknowledging unusual characteristics while refraining from unfounded speculation. Risk assessment for future interstellar visitors will benefit from the precedent set by 3 Atlas. The object's safe passage through our solar system, its consistent behaviour aligning with natural cometary physics, and the absence of any anomalous signatures provide baseline expectations for similar discoveries. Future objects that deviate significantly from this pattern might warrant different approaches, but the default assumption will likely remain that natural explanations should be exhaustively examined before considering more exotic possibilities. The educational value of the 3 Atlas investigation extends beyond its immediate scientific findings to demonstrate how modern astronomy functions as a collaborative, transparent, and evidence-based enterprise. The project has illustrated how institutions coordinate responses to unprecedented discoveries, how data sharing facilitates rapid progress, and how professional skepticism guards against both premature conclusions and reflexive dismissal of unusual phenomena. As we transition towards broader inquiries into cosmic perspective and humanity's place within the universe, the 3 Atlas investigation serves as a case study in how our species confronts the unknown. The emphasis on curiosity over fear, collaboration over competition, and evidence over speculation offers grounds for optimism regarding our capacity to manage even more profound cosmic discoveries that may lie ahead in the coming years and decades. Part 13. Scale of the Cosmos and Our Signals. The journey that brought 3I Atlas to our cosmic doorstep spans distances and timescales that challenge human comprehension. Yet, understanding these scales is crucial for grasping both the object's significance and our own place within the vast expanse of galactic evolution. When we refer to thick disk galactic origins, we are invoking a narrative that commenced when the universe was less than half its current age, when stellar populations differed dramatically from those we observe today, and when the Milky Way itself was still a nascent and chaotic stellar nursery. The thick disk comprises an older generation of stars that formed during the galaxy's early turbulent epoch, approximately 10 to 12 billion years ago. Unlike the thin disk where our Sun is situated, a relatively ordered region where stars follow roughly circular orbits around the galactic centre, the thick disk contains stars with more eccentric tilted orbits that reflect the violent conditions of their formation era. If 3E Atlas indeed originates from this ancient population, it carries within its core a record of stellar environments that existed long before our solar system was even a faint notion in a molecular cloud's imagination. The scales of this journey become almost poetic when we attempt to visualize them. 3 Atlas has potentially been traversing the galaxy for billions of years, a period during which entire generations of stars have been born, lived, and perished. Massive stars that existed when this object embarked on its interstellar odyssey have long since disintegrated as supernovae, enriching space with heavy elements and initiating new cycles of star formation. Planetary systems have formed, evolved, and potentially harboured life countless times over. During this ancient wanderer's sojourn through the cosmic darkness, the travel times involved dwarf any human conception of duration. If 3 Atlas has indeed been journeying for 5 billion years, a conservative estimate based on its apparent thick disk origin, it has been travelling for over 1,000 times longer than complex life has existed on Earth. Throughout its journey, our planet has witnessed the Cambrian explosion, 5 major mass extinctions, the rise and fall of the dinosaurs, and the eventual emergence of human civilization. Yet, from the perspective of this cosmic wanderer, all of human history represents merely the final microsecond of its multi-billion-year voyage. The distances traversed are equally staggering. Even at 3 Atlas's tremendous velocity of over 130,000 miles per hour, crossing significant portions of the galaxy necessitates millions of years. The object has potentially encountered hundreds or thousands of stellar systems during its wanderings, passing close enough to some to be influenced by their gravitational fields, perhaps even witnessing the birth of planets around stars that are now ancient giants nearing the end of their lifespans. These encounters would have been silent and unobserved, occurring in the depths of space, far from any witness capable of recording them. Each gravitational interaction would have subtly altered the object's trajectory, adding or subtracting kinetic energy in a cosmic game of pinball played across galactic distances. The cumulative effect of millions of such encounters could account for 3I Atlas's current extreme velocity, each stellar flyby contributing a minuscule nudge that ultimately accelerated this ancient wanderer to its present breakneck speed. The chemical diversity that 3 Atlas embodies takes on heightened significance when viewed against this galactic backdrop. Its carbon dioxide-rich composition may reflect formation conditions around a vastly different type of star than our own, in a stellar environment where distinct nuclear fusion processes, planetary system architectures, or interstellar medium compositions prevailed. The object serves as a sample of extraterrestrial chemistry, carrying molecular signatures from stellar neighbourhoods we may never visit directly. This chemical archaeology expands our understanding of galactic evolution in ways that conventional astronomy cannot match. While we can study distant stars through their emitted light and infer their properties via spectroscopy, interstellar objects like 3 Atlas carry actual physical samples of material that formed around those distant suns billions of years ago. It is akin to having fragments of alien worlds delivered to our doorstep, complete with isotopic ratios, mineral compositions, and volatile inventories that reveal the conditions of their genesis. Our own radiosphere, the expanding shell of electromagnetic radiation that announces humanity's presence to the cosmos, provides a humbling perspective on these galactic scales. Since Marconi's initial wireless transmissions in the late 19th century, our radio signals have been expanding outward at the speed of light, currently reaching stars within approximately 120 light-years of Earth. This appears impressive until we recognize that our galaxy spans roughly 100,000 light-years in diameter, rendering our radio presence a minuscule bubble in the vast galactic ocean. This radio bubble encompasses perhaps a few thousand stellar systems out of the galaxy's estimated 400 billion stars. Even our most powerful radio transmissions designed for interplanetary communication within our solar system would seem like faint whispers to any listeners around neighbouring stars. The notion that 3E Atlas might have been drawn to our solar system by our electromagnetic signature becomes implausible when we consider both the object's apparent age and the minuscule fraction of the galaxy that our radio presence occupies. The profound silence we observe when attempting to detect radio transmissions from extraterrestrial civilizations, the immense stillness underlying the Fermi paradox, becomes considerably less perplexing when considered against these immense cosmic distances. Even if our galaxy harbored countless civilizations capable of broadcasting radio signals, the sheer expanse separating them would render their transmissions incredibly faint and exceedingly difficult to pick up. The fundamental principle of the inverse square law, which governs the dissipation of electromagnetic radiation, dictates that doubling the distance from a radio source diminishes its perceived intensity by a factor of 4. This reality transforms interstellar communication into an extraordinary technical hurdle, demanding capabilities far beyond our present technological reach. The energy requirements for interstellar communication dwarf anything humanity has yet conceived. Transmitting a signal robust enough to be readily detected across typical interstellar gulfs would necessitate energy outputs on par with those of small stars. Even highly focused transmissions, akin to searchlight beams aimed at specific star systems, would require power generation capacities vastly exceeding anything currently achievable. These fundamental physical limitations likely explain why searches conducted by SETI, Search for Extraterrestrial Intelligence, have yielded no definitive artificial signals, despite decades of diligent listening across a broad spectrum of frequencies and directions. The same energetic considerations also apply to interstellar travel, providing crucial context for evaluating the feasibility of various hypothetical scenarios we've explored throughout this investigation. Accelerating even a modest probe to the speeds necessary for swift interstellar journeys would demand an energy expenditure equivalent to the total annual power generation of major industrialized nations. Larger spacecraft would necessitate proportionally greater energy investments, potentially surpassing the entire energy production capability of contemporary human civilization. The celestial phenomenon of the object designated Oumuamua's natural acceleration through gravitational interactions serves as a compelling illustration of how the galaxy itself can act as an accelerator for celestial bodies sufficiently patient to amass energy through repeated stellar encounters. This inherent cosmic mechanism offers a plausible explanation for the object's remarkable velocity without resorting to hypothetical propulsion systems or artificial acceleration technologies. The statistical implications arising from the discovery of interstellar objects become clearer when viewed through the lens of galactic-scale phenomena. If the formation of planetary systems routinely expels significant quantities of rocky and icy material, as computational simulations strongly suggest, then the galaxy should theoretically contain trillions of such errant bodies like Oumuamua. The projected discovery rate of several interstellar visitors annually by the Vera C. Rubin Observatory represents merely a minuscule fraction of this vast population, limited by the constraints of detection sensitivity, available technology, and the extent of observational coverage. This statistical perspective suggests that the observed chemical and physical variations within the small collection of confirmed interstellar objects may represent only a portion of the true diversity in composition and characteristics present within the galaxy's wandering population. Future observational surveys are likely to reveal objects possessing even more unusual properties than Oumuamua, thereby expanding our comprehension of the conditions and processes operative within distant stellar systems. The temporal scales of galactic evolution offer another essential framework for understanding the significance of Oumuamua. Over billions of years, the galaxy's chemical makeup has been progressively enriched as successive generations of stars have synthesized heavier elements from lighter ones, subsequently dispersing these products through supernova explosions. Objects that originated early in this cosmic timeline, like Oumuamua, assuming our age estimates are accurate, would reflect the chemical milieu of a younger, less metal-rich galaxy, vastly different from the stellar environments we observe today. This temporal dimension adds layers of complexity to the interpretation of chemical signatures observed in ancient interstellar bodies. The relative abundance of carbon dioxide that distinguishes Oumuamua from typical comets observed today might have been characteristic of objects forming around earlier generations of stars possessing different compositions and thermal properties compared to our Sun. Understanding these primordial formation conditions could furnish insights into the initial stages of galactic chemical evolution that would otherwise be inaccessible. As we approach the culmination of our inquiry into Oumuamua and its broader implications, these cosmic scales serve as a vital reminder of both the extraordinary nature of this discovery and the inherent limitations of our current vantage point. We are examining an object that has borne witness to galactic evolution across geological epochs, one that carries chemical imprints from stellar environments we have never encountered, and which provides a tangible physical link to processes that transpired billions of years before Earth itself came into existence. Nevertheless, despite its profound cosmic importance, Oumuamua remains fundamentally comprehensible within our established scientific framework. Its behavior adheres to the fundamental laws of physics. Its chemistry reflects natural terrestrial processes, and its trajectory is governed by the same gravitational principles that dictate the motion of every other object in the universe. The confluence of its exotic origin and its predictable behavior underscores both the remarkable diversity and the underlying unity of natural processes operating throughout the galaxy. This perspective, encompassing cosmic scale and natural law, provides the bedrock for our concluding reflections on what Oumuamua signifies for human understanding and our ongoing relationship with the vast cosmos that gave rise to our existence. Part 14. Hope Amidst Silence and Data. Perhaps the most profound gift that Oumuamua bestows upon humanity lies not in any speculative notions about its origin or purpose, but in the simple reality of its non-threatening passage through our cosmic vicinity. In an era when global challenges can appear overwhelming and our future uncertain, there is a deep sense of reassurance derived from a celestial visitor that arrives precisely when anticipated, behaves exactly in accordance with natural laws, and departs safely into the interstellar darkness without disrupting even a single terrestrial sunset. This reassurance is far from trivial. It represents the triumph of scientific comprehension over cosmic apprehension, the victory of meticulous observation over unsubstantiated conjecture. When Oumuamua was first detected hurtling towards our solar system at an unprecedented velocity, we might have harboured fears of the unknown. Instead, within weeks of its discovery, international teams of astronomers had accurately calculated its precise trajectory, meticulously analysed its chemical composition, and confidently predicted its harmless passage. This exemplifies human knowledge and collaboration at their absolute finest. The scientific bounty gleaned from Oumuamua has already surpassed what most astronomical discoveries yield over their entire investigational lifespans. The object's unusual carbon dioxide-rich composition has challenged our preconceived notions about typical cometary chemistry, compelling researchers to formulate new models to explain how the ratios of volatile compounds might vary among objects originating in disparate stellar environments. This is not merely academic knowledge. It directly informs our understanding of planetary formation processes that operate throughout the galaxy. The spectroscopic signatures revealed by the James Webb Space Telescope provide direct empirical evidence for the types of chemical processing that occur around other stars. The high carbon dioxide to water ratio observed in Oumuamua's coma suggests formation in proximity to carbon dioxide snowlines within protoplanetary disks, or alternatively, processing of surface materials by radiation over geological timescales. Either interpretation significantly broadens our comprehension of the diversity of environments and processes that shape icy bodies beyond our own solar system. These chemical insights carry implications that extend far beyond the realm of cometary science. Understanding the variability in volatile inventories among objects from different stellar systems assists astronomers in refining models of planetary formation and evolution, which are crucial for the ongoing search for potentially habitable worlds around other stars. If carbon dioxide-rich environments were prevalent during specific epochs of galactic evolution, this could influence the locations and temporal windows where we might expect to find conditions conducive to life as we understand it. The institutional response to Oumuamua has demonstrated the remarkable efficacy of modern astronomical coordination when confronted with unprecedented phenomena. The Pan-STAR survey initially detected the object. The Minor Planet Center then coordinated global tracking efforts. The Hubble and Webb space telescopes provided highly detailed follow-up observations, and ground-based observatories contributed complementary data, all accomplished within a time frame that would have been inconceivable just a few decades ago. This coordination transcends mere technological capability, representing a philosophical commitment to the principles of shared knowledge and collaborative investigation. The decision to make observational data publicly accessible through standard astronomical archives underscores the scientific community's conviction that cosmic discoveries belong to all of humanity, rather than to individual institutions or nations. Such openness becomes particularly significant when examining objects that, in principle, might represent our inaugural encounters with phenomena lying beyond terrestrial experience. The transparency that has characterized the Oumuamua investigation offers a robust template for how we might approach even more extraordinary discoveries in the future. Should astronomers eventually detect genuinely anomalous objects that challenge our fundamental understanding of natural processes, the established precedent of open data sharing and collaborative analysis provides the most effective pathway for distinguishing between observational errors, instrumental artifacts, and truly enigmatic cosmic mysteries. The public engagement surrounding Oumuamua has illuminated both the opportunities and the inherent challenges of communicating complex scientific concepts to broad audiences within our current media landscape. Legitimate scientific institutions have, by and large, succeeded in conveying both the object's unusual characteristics and the scientific consensus regarding its nature, effectively counteracting speculative narratives. The media coverage has educated millions about interstellar objects, galactic structure, cometary science, and the methodologies astronomers employ to study remote phenomena. However, the very communication channels that facilitate effective science education also serve as conduits for misinformation and conspiracy theories, which can profoundly distort public understanding of cosmic discoveries. The challenge of maintaining rational discourse concerning astronomical phenomena has grown increasingly complex, particularly as social media algorithms tend to prioritize engagement over accuracy, sometimes amplifying sensational claims at the expense of measured scientific analysis. The Oumuamua case study vividly demonstrates how scientific institutions can effectively navigate these communication complexities through consistent messaging, clear delineations between established facts and speculative interpretations, and persistent correction of misunderstandings. This approach serves as a valuable model for managing future discoveries that may present even greater communication challenges. Live tracking websites, public press conferences, and accessible educational materials have collectively positioned Oumuamua as one of the most publicly accessible astronomical discoveries in recent memory. Amateur astronomers have actively contributed valuable observations. Student research projects have diligently analysed publicly available data, and citizen science initiatives have successfully engaged thousands of volunteers in monitoring the object's brightness and behaviour. This represents one of the most encouraging trends in contemporary science. The speculation that has surrounded Oumuamua, including the various scenarios we've explored throughout this investigation, serves legitimate purposes extending beyond mere entertainment. Contemplating exotic possibilities compels researchers to think more critically about the distinctions between natural and artificial phenomena in space, fosters the development of observational tests capable of falsifying conventional interpretations, and reminds us of the inherent limitations of our current understanding. However, the true value of such speculation lies in its direct relationship to empirical evidence rather than its sensational content. The scenarios we've explored gain significance when they generate testable predictions or highlight critical gaps in our existing knowledge. They become detrimental when they are mistakenly equated with established facts or used to promote unwarranted apprehension about cosmic threats. The careful distinction between speculation and established science that we have meticulously maintained throughout this investigation reflects broader principles concerning the advancement of knowledge and societal responses to uncertainty. Scientific progress is achieved through the dynamic interplay between imaginative hypothesis formulation and rigorous empirical testing, between creative speculative thinking and disciplined evaluation of evidence. Oumuamua has provided an exemplary case study, illustrating how this process operates when addressing genuinely unprecedented phenomena. The arc of understanding that has characterized the Oumuamua investigation, from its initial detection through detailed analysis to the confident conclusions drawn about its natural origin, vividly illustrates the developmental trajectory of scientific knowledge over time. Early observations indeed raised intriguing questions regarding the object's unusual properties. Subsequent measurements progressively refined our comprehension of its composition and behaviour. Ultimately, a sufficient body of evidence accumulated to support confident conclusions regarding its nature as an ancient, chemically distinctive, but fundamentally natural comet. This progression from initial uncertainty to a state of informed understanding represents science operating at its most effective, demonstrating how patient observation and meticulous analysis can resolve seemingly mysterious phenomena. This process offers substantial reason for optimism regarding our capacity to comprehend even more exotic cosmic discoveries that may await us as our observational capabilities continue to advance. The promise of future discoveries looms large as we consider Oumuamua's position within the expanding catalogue of interstellar objects. The Vera C. Rubin Observatory's Legacy Survey of Space and Time is projected to detect hundreds of similar visitors over the next decade, effectively transforming interstellar objects from rare curiosities into commonplace astronomical phenomena. This statistical revolution will facilitate comprehensive studies of their population characteristics, chemical diversity, and dynamical properties, which are currently impossible given our presently limited sample size. Each new discovery will contribute essential pieces to the intricate puzzle of galactic evolution, planetary formation processes, and the distribution of materials throughout interstellar space. The chemical signatures that render Oumuamua unusual may prove to represent common formation conditions around specific types of stars, or they may persist as genuinely rare examples of exotic processing that occurs only under very particular circumstances. The technological capabilities that enabled the Oumuamua investigation, including highly sensitive wide-field surveys, rapid follow-up observations, space-based spectroscopy, and sophisticated global coordination networks, continue to improve at remarkable rates. Future interstellar visitors will be detected earlier, characterized more thoroughly and understood more rapidly than current examples. This ongoing progression of capability instills confidence that even genuinely anomalous objects would be recognized and studied with remarkable effectiveness. The broader context of cosmic exploration that Oumuamua embodies extends far beyond the specific details of this individual object. Each interstellar visitor effectively expands our direct sampling of galactic materials and processes, complementing the indirect information we gather through stellar spectroscopy and theoretical modelling. These objects serve as cosmic ambassadors, carrying invaluable information about stellar environments that we may never have the opportunity to visit directly. The philosophical implications inherent in studying such objects deserve recognition, alongside their undeniable scientific value. Oumuamua tangibly connects us to the profound history of our galaxy, to processes that unfolded before the existence of our solar system, and to chemical environments that shaped the very materials now traversing our cosmic doorstep. This profound connection offers invaluable perspective on our place within the grand tapestry of cosmic evolution and the unwavering continuity of physical processes across immense scales of space and time. As we prepare to conclude our comprehensive investigation into Oumuamua and its far-reaching implications, the overarching theme that consistently emerges is one of successful scientific discovery, guided by empirical evidence, enhanced by imaginative thinking, but ultimately firmly grounded in meticulous observation and rigorous analysis. This object has served to challenge our established assumptions, significantly expand our collective knowledge, and provide an exemplary case study in how modern astronomy effectively confronts the unknown. The most dire scenario that initially motivated our investigation, the possibility of cosmic catastrophe or alien invasion, has proven unfounded, supplanted by a more nuanced yet equally profound narrative of ancient chemistry, intricate galactic evolution, and the remarkable capabilities inherent in human scientific inquiry. In replacing fear with understanding, Oumuamua has perhaps offered the most valuable gift any celestial visitor could bestow, a clear demonstration that patient observation and collaborative investigation possess the power to illuminate even the deepest cosmic mysteries. Part 15. Good Night, Cosmic Messenger. As Oumuamua continues its ancient outward journey, gradually receding from our sun and fading with each passing day into the star-strewn darkness from which it originated, we are left with indelible images that will undoubtedly endure long after the object itself has vanished beyond the detection capabilities of our most powerful telescopes. The exquisite photographic renderings captured by the Hubble Space Telescope depict a star-like point of light, ensconced within the ethereal gossamer expanse of its carbon dioxide coma, a celestial Christmas ornament suspended against the infinite black canvas of space. The infrared vision provided by the Webb telescope meticulously reveals the intricate molecular signatures within that coma. Each spectral line represents a distinct word in the ancient chemical lexicon this visitor carries from its birthplace around another star. The trajectory plots themselves narrate a story of cosmic choreography. Smooth, elegant curves arc across diagrams, meticulously illustrating Oumuamua's path through our solar system, its transit past the orbit of Mars, its graceful arc around the Sun at perihelion, its outward trajectory towards the realm of the gas giants, and its subsequent continuation into interstellar space. These are not the erratic, unpredictable paths characteristic of human political or economic events, but rather the serene precision of celestial mechanics, as inevitable as the rising sun and as dependable as the changing seasons. There is a profound sense of satisfaction derived from this predictability, this inherent cosmic reliability that operates independently of human influence or control. While our terrestrial world is often beset by uncertainty, Oumuamua faithfully adheres to the fundamental laws that have governed motion in space since the universe's inception. Its departure is not dictated by human decision, but by the fundamental forces that shape reality itself. In an era frequently characterized by manufactured anxiety and artificial urgency, such cosmic dependability offers a profound form of solace. The answer to our investigation's central question, what is the worst-case scenario, has proven refreshingly mundane. There is no Hollywood-esque catastrophe awaiting us. No alien invasion threatens our civilization. No cosmic disruption will alter Earth's orbit or climate. The worst-case scenario, in terms of actual physical threat, is quite literally nothing at all. Oumuamua will depart our solar system precisely as it arrived, silently, safely, and in perfect accordance with the precise predictions of mathematical physics. However, perhaps characterizing this outcome as merely mundane overlooks its true significance. The very fact that we can accurately predict the behavior of an object that has potentially traveled for billions of years, that formed around a star we have never directly observed, and that carries chemical signatures from environments we have never studied firsthand. This predictability represents one of science's most profound triumphs. The laws of physics operate with such unwavering consistency that phenomena separated by cosmic distances and geological time still adhere to the same fundamental rules. The extraordinary nature revealed by 3i 2017 U1 or Oumuamua is no less captivating for its natural origins. Its chemistry, rich in carbon dioxide, challenges our preconceived notions of typical cometary composition, thereby broadening our comprehension of the varied substances that can coalesce in the vicinity of different stellar types. Its apparent origin within the thick galactic disk implies formation in stellar environments vastly dissimilar to our local cosmic domain, presenting us with a tangible sample of ancient galactic chemistry for meticulous study. These distinctive attributes have already begun to shape astronomers' perspectives on planetary formation, the evolutionary trajectory of comets, and the chemical tapestry of interstellar bodies. Scholarly works focusing on Oumuamua will undoubtedly be referenced for decades as researchers integrate its insights into more comprehensive theories concerning the genesis and evolution of icy celestial objects across the Milky Way. The scientific ramifications extend significantly beyond this solitary entity, shedding light on processes that unfold around innumerable distant stars. The hypothetical scenarios we've contemplated throughout this exploration, envisioning extraterrestrial technology, long-vanished civilizations, or esoteric physical phenomena, have served their purpose by stimulating our imaginative faculties and underscoring the types of inquiries that arise when confronted with genuine cosmic enigmas. However, the accumulated evidence consistently directs us toward natural explanations which, though remarkable, operate well within the established framework of physical laws. This conclusion should not diminish our sense of awe. The cosmos has already demonstrated itself to be sufficiently peculiar and magnificent through natural occurrences, from the enigmatic existence of black holes to the accelerating expansion of the universe. Incorporating artificial intelligence or advanced technology into this already astonishing reality might prove superfluous in achieving the profound sense of wonder and cosmic perspective that propels scientific investigation. The musical accompaniment to our farewell to Oumuamua should be neither foreboding nor celebratory, but rather contemplative, aiming to encapsulate both the mystery and the comprehensibility inherent in cosmic phenomena. Perhaps compositions like Gustav Holst's The Planets or Samuel Barber's Adagio for Strings could evoke the sheer vastness of space while retaining a resonant human emotional quality. The tone should encourage introspection rather than elicit excitement, fostering wonder instead of fear. Throughout this investigation, we have strived to maintain clear distinctions between validated scientific understanding and imaginative conjecture. The precise point where empirical data concluded and speculation commenced has been explicitly demarcated, enabling observers to differentiate between what we definitively know and what we can only envision. This commitment to transparency reflects not only intellectual integrity, but also a practical necessity in an era where erroneous information can disseminate with greater rapidity then fact-checking mechanisms can correct it. The ultimate message derived from our inquiry pertains not to the perils of impacts or invasion narratives, but rather to the more insidious threat of cosmic anxiety, the apprehension that surfaces when we encounter phenomena that elude our immediate grasp. Oumuamua has proven that such fears can be assuaged through diligent observation, meticulous analysis, and collaborative efforts among researchers dedicated to evidence-based comprehension. The concluding segments of our documentary should direct interested viewers to the abundant, publicly accessible information that facilitated this investigation. Official NASA web pages dedicated to Oumuamua offer authoritative summaries of observational findings. The archives of the Space Telescope Science Institute house the actual Hubble and Webb images and spectra that underpin our scientific comprehension. Professional journals and popular astronomy periodicals provide detailed technical analyses alongside accessible explanations for broader audiences. These resources represent far more than a simple bibliography. They embody the democratic ethos that has characterized scientific inquiry from its nascent stages. The decision to make observational data freely available through standard astronomical archives reflects a shared repository of knowledge that transcends national borders and institutional allegiances. Such openness offers a beacon of hope for how humanity might approach even more extraordinary cosmic discoveries in the years to come. The anticipation of future interstellar visitors imbues our farewell to Oumuamua with a sense of expectation. The Vera C. Rubin Observatory is poised to detect dozens of similar objects over the next decade, each promising to impart unique lessons regarding galactic chemistry, planetary formation, and the diverse population of wanderers that inhabit interstellar space. Some may exhibit even greater chemical peculiarities than Oumuamua, while others might present characteristics that challenge our understanding in entirely novel ways. Each discovery will contribute to an expanding database of interstellar object attributes, facilitating statistical analyses that are currently unfeasible given our limited sample size. The population characteristics, chemical diversity, and dynamical properties elucidated by these forthcoming surveys will inform theories of galactic evolution and planetary formation that extend well beyond our immediate stellar neighbourhood. The acknowledgements listing the observatories, archives, and individual researchers instrumental in the Oumuamua investigation serve a purpose beyond mere attribution. They serve as a reminder that significant scientific breakthroughs arise from interconnected networks rather than isolated brilliance, from institutional backing rather than solely individual inspiration. The synergistic coordination between ground-based surveys, space telescopes, and data repositories, which enable the swift characterization of this interstellar visitor, exemplifies modern astronomy at its most efficacious. As Oumuamua recedes into the cosmic expanse, propelled by the momentum accrued during its billion-year transit through interstellar space, it leaves behind more than just scientific data and published papers. It has provided a compelling case study in humanity's approach to the unknown, employing instruments rather than armaments, curiosity rather than apprehension, and collaboration rather than rivalry. These choices reflect our loftiest aspirations for engaging with cosmic mysteries that may ultimately prove even more profound than this ancient wanderer from the void between the stars. The ensuing silence following Oumuamua's departure is not one of emptiness, but of anticipation, awaiting the next cosmic emissary that will undoubtedly arrive, carrying its own unique chemical signatures from distant stellar nurseries, its own challenges to our understanding, and its own opportunities for expanding humanity's knowledge of the universe that gave us life. Within this waiting, within this persistent observation of the heavens, perhaps lies the most hopeful facet of our connection with the cosmos, the unwavering conviction that there are always more wonders to uncover, more questions to pose, and more reasons to gaze upward at the stars with curiosity rather than dread. The gentle fade to black that might conclude our visual narrative accompanies Oumuamua as it dissolves back into the stellar tapestry. No longer a distinct entity, it once again becomes an integral part of the cosmic landscape from which it briefly emerged. Its passage through our solar system represents a mere handful of months within a journey spanning geological epochs and destined to continue for countless more. We were granted the privilege of witnessing this fleeting cosmic moment, of studying this ancient traveller, and of adding its narrative to the ever-growing compendium of marvels that populate the space between stars. Good night, cosmic messenger. Thank you for the invaluable lessons, the crucial data, and the poignant reminder that the universe remains infinitely more peculiar and wondrous than our terrestrial imaginations might conceive. Safe passage on your continued voyage through the galaxy, carrying whatever chemical secrets and ancient memories remain locked within your nucleus, a testament to stellar environments and formation conditions that predated our world's first experience of its own star's warmth. Until we encounter your kin from other distant systems, from other ancient eras, from other forgotten corners of the cosmic wilderness that encircles our small yet remarkable planetary home,